Welcome back to our tutorial on meta-learning. I'm Joaquin van Schoren, and in this part, we'll talk about meta-learning in the context of learning over a distribution of tasks, so that with each new task, we can learn it better and faster. So machine learning, we have a number of tasks. These tasks give us a certain amount of data, and with this data, we can learn a model. We need a machine learning algorithm that takes data and some hyperparameters given by the user, and then initializes a number of model parameters. And then given the data, we optimize these parameters so that we get, we minimize the loss or we maximize the likelihood of the outputs. Now, if we have a second new task, say running, and if the previous task was walking, we obviously want to transfer information. Learn this new task from scratch would just be unrealistic in the amount of data and compute requirements. And humans can already do this very efficiently. We first learn how to walk, then to run, then to play football, and every new behavior we can learn more efficiently with the more experience we have. So we call this in general bias, some bias we transfer from previous experience. And there's a lot of proof from cognitive science, for instance, that shows that we actually learn these biases. We're not born with them. And humans are also very good at choosing new tasks. Right? We play and we explore and we're curious and we choose new tasks that allow us to learn better in general. So what can we learn? We've seen a trend recently from replacing hand-designed algorithms with learned algorithms. For instance, neural networks, embeddings, we can learn these very efficiently now. And this allows us to think about how far we can go. Can we really go towards general AI generating algorithms that can bootstrap themselves from very simple biases and then choose their own environments and learn better and better. There's a nice paper about this by Jeff Bloom. So this compels us to work on 3 parts. So one is to learn how to learn architectures, hyperparameters, structures, and pipelines, and so on. Once we have an architecture, we can think about, okay, how can we learn the model parameters efficiently? Are there priors or embeddings and so on we can use to do that, and how do we learn these? And the third is, once we have algorithms, what would be interesting new tasks to learn so that we become more general and can learn new tasks better? So in this talk, we'll talk about the second 2 aspects, and the next talk we'll talk about how to learn architectures and pipelines. So in meta-learning, more formally, we want to learn an inductive bias. An inductive bias is simply any assumptions that you give to the learning algorithm separate from the task itself. This could be priors, constraints, representations, model parameters, initializations, optimizers, and so on. Now, important is that this task, so that this bias is minimal in a sense that it should give the right amount of bias to the learner, not too little because then it won't learn faster, not too much because then it will overfit on the previous tasks, right, which we call meta overfitting. One way of doing that is by level optimization. So the idea here is that we take a learning algorithm and we take some aspect of it that we want to learn. For instance, how do we initialize the weights of a neural net? You could parameterize that, express that as a set of meta parameters theta, and then learn these parameters across tasks. Right? So if you have a group of tasks, 1, 2, 3, we want to learn a good initialization, for instance, expressed as these parameters theta. Now, this ends up being a bi-level optimization because these hyperparameters, these parameters theta, we put them into a learning algorithms, but then the learning algorithms still have to learn on the tasks, right? So say that we initialize a neural net, we still have to learn and fine-tune the model weights. So on the top level, we learn these meta parameters theta, and on the lower level, we learn the per task model parameters phi y. And in this case, we want to learn the optimal set of model parameters phi given the task and the meta parameters we gave to it. The nice part about this approach is that once we have a new task, we can then again imbue the learner with these meta parameters, which we've learned before, but we're also able to then fine tune further this learner on the new task. This is a bit more in detail. So we learn these meta parameters with a meta learning algorithm. This could be any meta learning algorithm that can this parametric, right? It needs to express meta parameters theta, which will be the model parameters of this meta model. It has a meta optimizer, F meta, and a meta loss meta. The meta learning algorithm learns these parameters theta, gives them to the base learning algorithms, which will then use them to instantiate models, train on the tasks. This is our inner training loop. And after the model has been trained, we get a final error and we give that back to the meta learner, which then computes a meta loss over a group of tasks. And then uses that loss to optimize its own parameters theta. When it's done like that, when we've done meta training, we can do meta testing, which means we give the optimized parameters theta to the learning algorithm, which can use them to instantiate a model, but is then also able to further fine-tune its own model parameters on the new task. Another way of doing this is with black box models. So these are models which have also high parameters theta, but they are internal. They're not part of the learning algorithm. They're just part of the meta learning algorithm itself. And what the meta learner wants to do is, given a task, given the training data of a task, predict the model parameters which will be ideal for solving that task. Right? So we give the task itself, or at least the training data of the task, to the meta learner, which will then learn an embedding of these tasks, produce a meta model based on a number of hidden parameters theta, get a loss, and then meta train until it finds better internal parameters theta. It gets a signal from predicting the per task parameters phi, and in the learning algorithms, they just feed forward. They just build a learner with the predicted model parameters, and from that obtain a loss, and then the loss over all the different tasks are given to the meta model. So in this case, there's no learning happening on the per tasks, only in the meta learner. When it's done training, it can then make predictions. So if there's a new meta test task, we give again the training data to the meta learner, which will then predict the optimal per task model weights. And then the learning algorithm will again feed forward, use them to build a model, and we're done. So there's no training or fine tuning happening anymore. So we also call these amortized models because there's no training and meta test time. It's also called learning fast by learning slow, because obviously they're fast at predict time, at meta test time, but they're slow at meta train time because they have to learn a lot of times to learn this transformation. This is also related to hypernetworks. So hypernetworks are networks that predict the weights of other networks, and you can see the meta model here as a type of hypernetwork, right? It produces the weights of another network, with the clarification that in this case, the embedding for the tasks is learned by the meta learner. Let's see a few examples. So the first example is future learning. So in that case, we are given a number of tasks. So two classes, cats and dogs. And for each class, we have 3 shots, 3 examples. So 3 examples of cats, 3 examples of dogs. That's our training set or support set. And then given a new image in our query set or test set, we then have to classify it only based on these examples. Okay. I will always make it clear when I say training set and test set, I mean the base training based test. Otherwise, I'll talk about meta train. That's the collection of tasks, or meta test, the collection of test tasks. Okay, so we can solve this first of all with bi-level optimization. So we have meta learner that, for instance, wants to learn the initial model weights per task. So it learns these, and then the learner learns on each of these tasks, gets the loss, and then over a group of tasks, we combine the loss into a meta loss, which is used to optimize the meta learner. Right? So it learns an initialization of weights. It can also learn an optimizer. It can learn some kind of metric and so on. So we'll see more details soon. Now at test time, we can dispose of the meta learner, and we only need the learned model parameters, meta parameters theta, which you then give to the learner and which it can then use to build a first model and then fine tune that model based on the few examples that it still gets. Right? So it has to learn a model, in this case, on 6 examples only. But because of this initialization, hopefully it can do that efficiently. If you would use a black box model, it's a bit different. So in that case, the meta learner has access to the training tasks. It uses that to learn this transformation between the task, an embedding of the task, and the per task weight 5. And so when this is given, the learner can again feed forward, be instantialized, test it on the test parts of the train tasks, and then we get a loss, and then we combine that to learn this meta learner. Now at test time, meta test time, we again need the meta learner to produce these per task parameters phi given a new test task. Okay. We can also look at another example for meta reinforcement learning. So in this case, our tasks are these behaviors. For instance, picking an object here and putting it there, or putting an object there and putting it here, or pushing an object or opening a drawer and so on. So for each of these tasks, it can be, the initial state can change, right? So sometimes the initial state is here, sometimes the initial state is there, and that changes the task. At test time, we can either have the same tasks with different initial states, or we can have a new task which is similar, right? Like drawer opening instead of drawer closing, or sweeping instead of pushing, and so on. Otherwise, it remains the same. So the meta learner, the meta reinforcement learning algorithm here, again, has to learn from this theta. In this case, this parameter theta could, for instance, be the weights of the policy network. This could either be fixed, or you can sometimes you can fix some of them and still learn others. And so when the learning, the RL agent here gets these parameters and has a policy network, it can then construct trajectories, right? So it has learning episodes. It gives, it gets initial states, does actions, gets new states. Ultimately, after trajectory, it gets a reward. And then the effective policy, which we obtain, which is modulated on the weights phi, leads to a reward. And that reward we can then transfer to the meta learner, which gets this reward over a number of tasks and is then able to learn the policy for a group of tasks. Or at least learn the parameters phi for that. Again, at test time, we can we only need the optimized parameters theta to give to the meta learner, to the reinforcement learner, so it can learn effectively on few examples. We can also again do this with a black box model, in which case the meta RL agent actually has access to the training tasks. So it can engage in a number of train episodes to learn the task and then learn, well, for each new training task, pass the correct parameters phi to the RL agent, which then can learn fast, right? Because it's given phi, it only needs a few test episodes to learn a task, learn a policy. At test time, you can again need both the meta RL algorithm and this can construct the weights for the fast RL agent for solving a particular task. Now, there's a range of different meta learning techniques and different ways to build a taxonomy of them. In this case, we'll use one created by Hospitales et al., where we look at the meta learning algorithm, and like any machine learning algorithm, meta learning algorithm has 3 components, basically representation, like what do the meta parameters represent, an optimizer to learn these parameters, and an objective to optimize towards. One example is, for instance, to learn the initial set of weights or the initialization of the weights of a neural net. So instead of starting at a random point, a random set of weights, we meta learn what would be a good starting point for our network, so that we only need a few steps of gradient descent to find a really good model. Another approach would be to learning optimizers. In that case, we replace normal backpropagation with a learned optimizer, which can hopefully learn or find a good minima given a few number of updates. There's many more things we can do. We can learn black box models, we can learn embeddings, we can learn high parameters or architectures or losses. Instead of gradient descent, we can use reinforcement learning or evolution. Instead of having this manual future learning or multi or single tasks. So multi-task is more common. Single task is when you subdivide the task internally. You can have fast adaptation when you want to have a good model after only a few iterations, or if you don't care about that, maybe you want to look only at the performance after 1 million of iterations, or it could be online or offline. There's a whole range of different meta learning techniques that you can build, different applications as well. For now, there's 2 very good surveys you can read about that on top right here. For now, we'll look at a few key strategies that are good to know about. First, the gradient-based methods. These are exactly as we discussed before. So typically here we want to learn a model initialization phi init. So you can see this as learning a representation that's suitable for many tasks. It's like learning a pre-trained CNN instead that we want to learn all the parameters of the network. Also, with the constraint also that we want to maximize rapid learning. Right? So we want to find an initialization for a group of tasks so that we only need a few gradient steps, few gradient descent steps at test time to find a good model. Right? So the fine-tuning should only take a few examples. Now, each task I we give will lead to a task-adapted phi I. And we use the loss based on that to update the meta parameters theta using gradient descent and using an update rule that we can define based on meta parameters theta and the training set. And then after we have learned theta, we can still fine tune it on the test task with the same update rule. The most common, well-known algorithm here is MAML. So MAML works by taking a number of tasks, taking an initial set of meta weights theta, and then we do k steps of gradient descent. So if we start here, we go 1, 2, 3. If k is 3, we find an approximation of the optimal value for that task. And then at that point, we'll look at the test set loss, and then we compute the derivative of the test set loss with respect to theta. Then we update the per task parameters, 5i, as the original starting point minus a learning rate, alpha, times the gradient that we have observed at that optimal point. ID being that if we move this way, then hopefully by doing gradient descent again, we'll end up again at a better point in a few number of updates. And then we do this for every task. So in this was task 1. For task 2, do the same thing. We end up here. We compute the derivative of the test loss here. We have an R phi 2 over here. And then we learn a meta gradient, which is based on the derivative of the test loss for each of the tasks. This is not simply the sum of these because this is a second order gradient. So because we move from here to somewhere else, of course, phi optimal will also change. Right? So we need to back propagate from here all the way back to theta to learn how changes in theta will affect the gradient at the new point. Right? Once you've learned all, this will be a second order gradient that you need to compute. So this will be expensive. At meta test time, after we've learned that, we can, of course, learn very fast. We only need a few steps of gradient descent to then find a phi that's specific to our new test task. This is an example for reinforcement learning. So say that after we've done meta training, we end up with this agent, this AND agent. which has not yet given a goal, right? So the goals could be, for instance, to reach a certain velocity or to move in a certain direction. At time 0, it has only learned a good initialization. So it will just move around a bit. And then after we give it a goal, you can see that it can learn that goal after just one step, right? So if I start this, so you can see, again, this is just moving according to the learned optimization. And then when we give it a goal, like stay still, it can learn this quite well in a few number of steps. Or if you say move fast, then it can also learn that. So by having initialized this guy, giving it a good starting set of weights, we can then learn with just one update very fast. Right, so this has been a very influential algorithm, and there's many different variations of that. Some of them do things like learning weights per parameter, because obviously in neural nets, some parameters are more important than other ones. And so we can learn different weights for different parameters, which will effectively lead to different learning rates for different parameters. And which is reminiscent of many ways to improve gradient descent. We can also do things like curvature and warping, where we change the shape of the loss surface so that at test time, our gradient updates will be very fast, will be better. There's also an online version called Follow the Meta Leader, which works for online tasks. How scalable is this? Well, we have already observed that this is a second order gradient. So this will be quite expensive. Plus it will be very memory intensive because we're learning millions of parameters and we have to backpropagate. So every time we have to learn, we have to store a copy of all the network's weights in memory. So that will be also expensive. So there have been some improvements, or well, not improvements, but with faster versions of MAML. The first one is first order MAML. And this just replaces this second gradient with the identity function. And what this means is that this update rule now effectively becomes replace theta by the last step in our Kate step in gradient descent, right? So if the last step went from here to here, we just copy that, and then the new theta ends up here. Reptile is another approach. So what that does, it says, okay, if the approximation of the optimal for task I is here, we'll just move in that direction. So it's deadly simple. And so it will effectively be 5i star minus theta, and then times a learning rate beta, and then it moves in this direction. And it does this for every task sequentially. So it doesn't wait until n tasks are done. It does this task after task after task. In the first order MAML, the meta gradient is just the sum of the gradients per task. Another way to scale up MAML is called implicit MAML. So instead of doing this backpropagation, what we do is we just use the derivative at the observed maximum 5i. This is, of course, this can be bad if 5i is far from theta, right? Because the gradient will be very different. So to correct for that, we simply add a penalty based on how far 5i is from theta. So if it's very close, we think that we can trust the gradient. If it's very far, we cannot trust it so much, so we have a larger penalty. This leads to this objective. So we add this penalty term with a regularization parameter lambda, just as in rich regression. And this happens to have a closed form solution, so this can be computed much faster. Okay, how generalizable is this? Well, there is first of all a universality proof that tells that MAML is very expressive. It has also been shown to be very resilient to overfitting, especially on small tasks, small test tasks. Other work has found that the effectiveness of MAML is mainly due to feature reuse. And they've shown that by taking the learned parameters theta here in a convolutional neural net and freezing theta for all layers except for the last one, as we only fine tune the last layer. And this turns out to work almost as well as fine-tuning all the parameters theta. Right? So this tells us that it's a big part of this ability to learn fast is because it learns a good embedding of the data, basically. Based on that, you can also think about, okay, what happens if we just learn embedding? Right? So it has been shown actually that if you combine the entire meta training set into one big task, and you learn embedding on that, then you can still do featured learning by using a simple learner, not a neural net anymore, but like a simple linear logistic regression, for instance. And then train this guy on a few examples, and it shows that given a good embedding that you've learned, there are some extra tricks involved, but once you've learned this good embedding, you can actually outperform many of these meta learning techniques. Now, with the caveat that this is only for few-shot learning benchmarks, which admittedly is kind of a special case, right? Because they're all from this very similar distribution. This probably won't work on cases where the test tasks are much less similar to the training tasks. Related to that, it has also been shown in MetaRL that MAML works well, but only for tasks where you only need a few actions at test time. But you can fix that by adding an exploration term to the objective. And this way you can still, it's called eMAML or exploration MAML, where you force it to actually also learn larger goals at test time, longer term goals. Okay, there's an interesting Bayesian perspective on this as well. So if we view a normal meta learning as such, so we have our meta parameters theta or per task parameters phi, and then we predict x, y given x, right? And this is what we've done before. We sample from the task distribution, we fine tune phi, we produce the test points, and then based on the loss, we update theta, right? And at test time, we get point estimates of prediction. In the base case, ideally what you would want is an uncertainty of the predictions. If your set of training tasks is very similar, then you can be more certain than when your set of test tasks is very different from each other, right? Or when the test task is very different from your training tasks, again, you would want your predictions to reflect that, right? To have more uncertainty. And so a fully Bayesian approach will be able to do that and produce these kind of predictions. We don't only get an estimate, you also get the uncertainty for that particular task that you want to learn. Now, of course, computing these is intractable, so we need some kind of approximation. One thing you can do is empirical based, so you can fit a point estimate on theta, learn it from the data, and it turns out that you can then express the per task parameters phi as you can factor it as a product of a likelihood and a prior. So the likelihood of y given x and phi, and the prior phi given theta. Right, so you have a likelihood around phi and then a prior around theta. Now, it also turns out that when you use theta here as the initialization of gradient descent with early stopping, so you stop after k steps, this is approximately equivalent to placing a prior over the task-specific parameters. Right? So we know that the optimal point should be somewhere here around phi. And the standard deviation depends on k, the number of steps, and the learning rate. It's actually the case that the smaller k is, the less likely you are overfitting. If you make k very large, then you're more likely to overfit. Now, interestingly, this is exactly what MAML does. Right? It estimates phi with k steps of gradient descent, and it updates the prior theta to make it easier to optimize phi. So this is a very nice equivalence. Of course, this still doesn't give you uncertain predictions. So to do that, you need a fully Bayesian meta learning approach. Right? So to do that, you need some kind of approximate method. So one thing you can do is some solving technique with variational inference. And one example here is platypus, which you see here. And so you can see that given some data points, it learns not only the mean, but also the certainty for all predictions. There's some other work, that's Bayesian MAML, and got this one. I think it's amortized Bayesian meta learning. You can also use a plus approximation, then you get Llama by Aaron Grant, and you have variational approximations of the posterior. These are more complicated, but these are called like the neural statistician and neural processes. Now, what if our tasks are not IID, right? So our test tasks are very different from our trained tasks. We can still use this Bayesian approach by using specific latent variables Z, and conditioning phi also on Z. This allows us to impose additional structure on it. And there's some very interesting work that shows you that you can actually do this to learn tasks which are very different from what you saw at train time, or somehow different. Okay, a second thing you can do next to learning and initialization is to learn an optimizer, right? So this is a very old idea. It goes back to the 90s. Where there was some work, for instance, by Benjo on learning bio-inspired update rules. There was learned from Schmidhuber in '92 about fast weights. So here the weights of the network are learned by another network that continuously changes the weights of the base network. More recently, there's been work by Hochreiter, for instance, where they replace the update rule with a neural net, right? So phi is phi minus a learning rate times some number produced by a neural net given the task. And so we have to learn a set of meta parameters theta, which is exactly what we've been doing before, right? So it's again a gradient-based method, but instead of learning the parameters as theta, we learn parameters of the update rule as theta. A modern version of this was proposed by Andrišević, which is basically a more scalable version of this LSTM ID, which looks a bit like this at the bottom here. So we have a meta learner that has to learn some parameters theta, and these parameters theta define an LSTM, which is then used to optimize an OptimiZ model. So the OptimiZ has certain per task parameters phi. The optimizer gets the value, computes the gradient, and returns an update rule. And then does this over and over and over again until we have some test point. We backpropagate through time, we compute the loss, we use the loss to update the meta learner, and that way the meta learner can learn a good set of weights theta to give to the optimizer. So what we're effectively doing is we learn an optimizer that works well on a number of tasks on the same distribution. So the OptimiZ changes with the optimizer, stays the same, and gets updated with new parameters theta over time. This has been shown to work for image classification and also for future learning. But you can also learn other optimizers. First of all, a very interesting finding is that if you look at what these LSTMs and RNNs learn, you can see that they learn something that looks a lot like momentum and gradient clipping and learning rate schedules. For instance, here we can see a learning rate schedule. So you see there's like a warm up and a cool down. These are optimizers for, I think, logistic regression. And so they learn schedules. And here you can see it learns something like learning rate adaptation, right? So if the gradients are small, then you should use a high learning rate. If the gradients are large, you use a small learning rate, which is very similar to what happens, for instance, in RMS prop. Right? But we didn't tell the optimizer to do that. It just learned that from data. There are also RL-based optimizers. It's a nice paper called Learning How to Optimize. So here they learn optimizers for instance, linear models and simple neural nets. And they use reinforcement learning. They use guided policy search to learn a policy to update the weights of, for instance, a linear classifier. You can also add an optimizer to MAML. So then you do both initialization and optimization in a fully gradient-based way. So, for instance, you can do this for learning different learning rates per parameter, as we saw before, or you can learn how to warp the loss surface to get better predictions at test time, or better adaptation at test time. There are also a number of black box optimizers, which typically replace like other black box optimizers, but you learn them on data using an RNN. Like, for instance, if you would normally use Bayesian optimization to update your hyperparameters, you could also learn how to do that using RNN. It's another interesting piece of work where they have user-defined priors. So if a user can give you some kind of prior, you can give that to, you can learn an optimizer based on the prior. So there's a way of adding bias to a model that you cannot, adding bias to an optimizer that you cannot learn from the data. Another very interesting piece of recent work by Luis Kirsch is how to speed up backpropagation by meta-learning, sparsity, and weight sharing. Right? We all know that sparsity and weight sharing help, but we don't always know how to do weight sharing. So here we just meta-learn how to do weight sharing, and it also seems to work very nicely. Okay, another class of techniques is metric learning. So here what we do is we want to learn an embedding network based on parameterized on theta again, that transforms the input data, detrain and detest. And we learn this embedding across all the tasks, right? So given inputs like flower, bird, we learn an embedding for this. And we do this over a number of tasks. And when we've done that, every input becomes a point in this embedded space. And then you can use very simple models to make predictions. For instance, you can learn a classifier, a linear classifier, to predict between birds and flowers, or you can use something more like KNN-like, where you look at the similarity or distance between points to make a prediction. Right? This can be seen as their own set of approaches called non-parametric approaches. If you squint a bit, you can also see this as a black box model, where this model G conditioned on theta produces these embeddings internally, right? And then predicts the model parameters of, for instance, a linear classifier. But of course, this could also be non-parametric like KNN. Okay. There's a number of ways to do this. So one simple way would be to use time-based networks. An improvement on that is matching networks. So here, so say we have four classes of dogs here, blue, yellow, orange, and red. And then we have a test example here. And now we want to classify this. So the simplest way of doing this is to learn embedding, right? That embeds these images as a vector. We use the same embedding for a test case, and then we just have some kind of distance function between this one and the ones per training set. Now, the way that this is done in the simplest case, G and F here are the same. They produce the same embedding, and we use a simple cosine similarity between the vectors, and we push it to a softmax to get a probability over all the classes, and then we predict the one with the highest probability. If there is some context, like if the test cases don't come randomly or not IID, we can also learn a contextual embedding, in which case G is the bidirectional LSTM and F is an attention LSTM. Another approach is very popular are prototypical networks. They're even simpler. So what you do here is you learn embedding that encodes each data point. So each data point becomes a point in this n-dimensional space, depending on how much dimensions you want in your embedding. And then you define a prototype for all the examples of a certain class. Right? So if you have a class C1, we look at all the examples of C1, we see where they are, and then we learn a prototype, which is the average of them. We do the same for class 2, for class 3, and so on. And then at test time, we again embed our test point, and then we see where it's closest to, right? So the class distribution is based on the inverse distance between X and all the prototypes. And again, we define this as a softmax So we have a probability over all the different classes. The distance function can be any differentiable distance. For instance, squared Euclidean is obvious. And then they use normal log-likelihood maximization to learn the embedding. Now, instead of choosing a distance function, which is kind of a heuristic, you could also learn the distance function. That's the idea behind relation networks. So they also start with an embedding of, in this case, the images. So every image becomes an embedded vector. But then instead of saying use Euclidean distance, they learn a distance by first concatenating the vector of each input image with our test image. And then we learn how these images relate to each other. Right? And then this is expressed as a relation network G, which has to learn another set of parameters theta, metaparameters theta. And once we've learned that, we have learned a new distance function, and then the rest is as usual. So for each, you just use this parameter, this model G, to then predict which training point is closest to this test point. This is more expressive because you can actually learn nonlinear relationships between the images. Okay, there's quite a few other techniques you can use, like Siamese networks. There's also graph neural networks in which every training point is a node, and then there's the edges of weights, so it's fully connected, and there's a propagation rule that then learns the weights between each point. The nice thing here is it's also applicable for semi-supervised and active learning, while all the others are only really applicable to feature classification problems or maybe regression problems. Another approach are attentive recurrent comparators. So the main idea is that if you have an image A and image B, instead of comparing them directly with each other, you look at patches. Just as a human would look at certain aspects of the images, it does something like that. It looks at patches and see if these patches match some patches in the other image. So it uses attention and the context. There's also a model called MetaOpNet. And in this case, you learn embedding specifically to then use a linear model to distinguish between classes. Overall, these techniques they're very fast at test time, so they're useful for future classifications. They have fewer applications outside of future learning. And they often fail when the test tasks are more different than the training tasks, right? So they really depend on the similarity. The main reason for that is that they have no way to adapt. I mean, at least with gradient models, gradient-based techniques, we can still adapt. We can fine-tune towards the test task. With method learning, this is not possible. So just stuck with whatever we learned at method train time. Okay, a very interesting approach is black box modeling for meta-reinforcement learning. So in this case, we have a task. In this case, for instance, we want to pick and place with some certain goal. We have a meta-reinforcement learning algorithm that is given training task, and it has time to actually try different things on this train tasks, right? So it's given a large number of tasks, and it learns kind of which policies work well. When it has learned that it can transfer, well, anytime it can transfer a set of weights phi, and these weights phi typically are the weights of a policy network, like an RNN. You give them to an RL agent, which we call a fast RL agent, right? Because it has to learn fast. It only gets a few episodes to train on the train tasks. After a few episodes have been used, we compute the effective policy, right, modulated on phi. And then we can compute the reward, and then we combine the rewards over different tasks, and then we update the meta-RL algorithm, and that way we can learn this. At test time, we then have our trained RL. It looks at test cases, produces phi, and then our fast RL agent can use that to learn fast. If you look at the bottom right here, you see that the training task is in blue. So you get a starting condition, starting state, initial state. Our agent then has an action, and then every reward and new state updates some hidden parameters. And the agent can do this for a number of episodes. And then after a number of tries, like if it gets 2 tries, it ends after 2 episodes. And you reset the hidden state and you try again on another task. So RNNs basically say these RNNs serve as some a dynamic task embedding. So the RNN of the meta-RL algorithm kind of learns an embeddings for these tasks. And then they maximize towards the expected rewards in each trial. This is very expressive, so definitely very powerful. The problem that we still see is that longer horizons are still difficult, typically because RNNs have a limited memory capacity, so it's not easy to learn problems which require many actions. There are some other black box models that try to solve this. They're typically not so easy, so we can't explain them in full. Just to give an overview, there are model augmented neural nets. They use neural Turing machines, which are complex networks with short-term and long-term memory and external memory as well. So they're quite complex. There are meta networks. They're a bit more simple. So they have a base learner and a meta learner, and the meta learner has to learn the weights for itself and for the base learner. So this is related to the fast weights ID. And then you have the simple neural attentive meta learner. And this actually directly addresses this problem with RNNs having having limited memory capacity. So what they do is they replace an RNN with a series of 1D convolutions, as you see on the right here. So you can basically choose how much memory you need, and then you can learn either a supervised learning problem or a reinforcement learning problem. Finally, one last thing about training task as acquisition. So it's important to realize that what meta-learning actually does is it translates constraints on the learners to constraints on the data, right? So if the learner doesn't learn fast enough, we parameterize some aspect, and then we learn that aspect on the training data. That means that we are limited by how much information that training data can give us. Right? So if our training tasks have not enough information, there's not so much we can learn. Right? So this is a really good reason to think about, okay, how should we create those training tasks? Right? If we can build better training tasks, we can learn much more complex things. So the idea is, like, can we automatically create new tasks to inform and challenge our meta learners? There's a few research in this area. One is the paired open-ended trailblazer. So that does, it constructs a parameterized environment, so theta e. And by changing these parameters, theta e, we create different environments. Right? And then we likewise parameterize our agents, theta a. And then we select agents that can solve the challenge. Right? So initially, we have one agent and one environment. We train different agents. And then if an agent is good enough, we transfer it to a larger world where we evolve E into E1, E2, E3. And then we transfer this agent. We also generate new agents to learn on this more complex environment. And then when we get agents that are good enough here, we can then evolve our environments. So the idea being that the environments evolve at the pace that the agents themselves evolve, right? That's a very powerful idea. So one problem with this is, you can see it here, so it's a bipedal walker. And basically here this is already pretty good, right? The idea basically that if the learner gets better, then also the environments become more complex, just to keep it challenged. One problem with the PODE approach is that it has limited expressibility, right? So it is parameterized with theta e. So this puts some limitations on how expressive these environments can be. Of course, you can make theta e very large, and then gives you some more oxygen to work. Instead of that, what you can also use are generative teaching networks. So these are known, for instance, from dataset distillation. So say you have a large data set, you want to construct a smaller data set, which may not make sense to us, but will cause learning to be more efficient. What a generative teaching network does is it learns to generate such data sets, but it also meta learns the generator, right? So the generator creates tasks for the learner, then you look at the meta loss, and then we use that to update the generator over a number of tasks. So the generator actually learns to create good test problems for a certain given problem. The careful thing is that, of course, that it could generate anything. So we need to be careful that doesn't just generate noise. It needs some grounding in reality. But in any case, these are all very interesting and exciting paths towards the future. Welcome back to our tutorial on meta-learning. I'm Joaquin van Schoren, and in this part, we'll talk about meta-learning for automated machine learning. So just to recap, in the previous part, we discussed how we can learn how to learn algorithms and how we can create new environments. One thing we left open is that in these cases, we kind of assume that the architecture was already fixed. In this part, we'll see how we can also learn the architecture that's ideal for learning the new task. So again, our high-level view, remember that our learning algorithm does not only have model parameters, it also has hyperparameters, which are typically set by the user. I'll use hyperparameters in a very general way, in which I mean the normal hyperparameters, like for instance, the learning rate, but also the neural architecture itself. And if you have a pipeline of operations, for instance, including preprocessing, then this is also part of the hyperparameters. So loosely speaking, it's everything that the user has to decide. So roughly speaking, you can say that when the new task is very similar, you may not need to optimize the hyperparameters. You may just do them fixed and just learn or adapt the model parameters to the new task. However, if the new task is quite different, well, the more different the task is, the more likely it is that we need to adapt the hyperparameters, and maybe we even need to adapt the entire model. As a side note, note that we can also learn the hyperparameters and the model parameters phi at the same time. That's called bi-level optimization. We'll come back to that in a minute. So automated machine learning aims to automate the tasks that humans currently have to do manually. Right. So typically, if you're given a new task, a human expert has to use his or her experience to then decide how to build a number of models, pipelines, or architectures. Then it evaluates those, looks at performance, and then makes another informed guess to build a new model. And this requires a lot of expertise and a lot of time, and it's also often quite tedious, especially when you need to fine-tune some parameters. And sometimes you change a small thing and your performance drops to zero. So it's very tedious to do this kind of work. And AutoML wants to automate this in a data-driven, intelligent, and purposeful way using learning and optimization. So for example, one very typical scenario is that you have to build a machine learning pipeline. You're given some input data, and then you have to preprocess it. You have to extract features. You have to choose learning algorithms. You have to impute missing values and so on. So all these steps, you need to decide how to do them. On top of that, all of these steps also have their own hyperparameters. For instance, you can have 100 different ways to feature selection or feature extraction. And yeah, you need to decide how to do that exactly. And on top of that, the architecture of the pipeline itself can change. So you need to optimize both structure and the hyperparameters of your pipeline. And then you're still not done, because when you then deploy it in real life, your data may change over time, and your hyperparameters, which were optimal before, may have to be re-optimized because the data has changed, or maybe even have to change the pipeline itself. So you can see this is a very large search space, and it requires a lot of expertise to do this well. In neural architecture search, it's a similar problem, but just on graphs. So in this case, you have to decide the architecture of the network. You need to choose which are the layers, the operators you have. For each of these, how many nodes do they use? If it's a convolutional net, what are the filter sizes? If it's a deep net, do you need skip connections? Do you need pre-trained layers or transformers, and so on? And on top of that, you also have to decide the other hyperparameters, such as the gradient descent, hyperparameters, regularization, batch normalization, dropout, all these decisions. And each of these decisions can have a huge effect on the performance of your model. So AutoML aims to automate all these things using intelligent search algorithms and learning. Now, still, this search pace can be huge, right? So your AutoML method may have to spend a lot of time and try hundreds of models, sometimes even tens of thousands of models before it can find a good one. Right? And so the question we want to ask now is, can we do meta learning on this? So can we transfer a bias? Can we learn priors and use meta knowledge and maybe even use human priors and preferences into a self-learning AutoML system that can then do this much more efficiently and maybe just after building a few models already find a good model for you to use. Now, as an overview, we'll break this down into three kinds of things we can do. For a larger overview, you can see the survey. And this talk will focus on three typical ways of doing this. First of all, we can learn hyperparameter priors. So if uninformed, we would have a very large, complex hyperparameter space. Remember, hyperparameters plus architectures plus pipelines and so on, right? So you want to learn based on which configurations you've tried before, which hyperparameter settings you've tried before, and what the scores were. Put it into a learner, and then the learner has to give you a simpler hyperparameter space, in which it will be much easier to find a good model. Okay? So we want to learn these priors. So which are typically the good things to do, right? Which are the most important things to pay attention to. Right? And if we can learn that, then we only have to learn, search a small subspace of this very complex space. Another thing you can do is warm starting. So instead of starting randomly with a random configuration, like a random architecture, you can learn from experience and start with an architecture or a pipeline that probably worked well on similar tasks, right? So this is related to metric learning. So in this case, we're going to put on the hyperparameter level. So we're going to look at which are similar tasks, and if we find them, maybe we can try the things we tried on that worked well on these similar tasks. And finally, we look at meta models. These are models that are trained to build entire new models or to learn a certain component like an activation function. Okay. First, I'm going to start with an observation, and that's that current AutoML systems already strongly depend on learned priors that we put into the system. Right? So typically, current AutoML systems are only possible because we have observed certain trends in what makes models work well, and we put that information into the models as a kind of prior. So for instance, if you look at pipelines, there's typically a certain recipe for building a good pipeline. Right? It typically starts with preprocessing. So first you do scaling, then you do encoding, then imputation, then class balancing or instance balancing. Then you do preprocessing, and then you choose a classifier. And if you're done with that, then you can ensemble or stack multiple classifiers together into a larger model. And so if we know that this is the typical structure of a pipeline, we can put that into a prior that we give to our AutoML system. So we do this typically by fixing the architecture. So we say that this is the only way that you can build a pipeline. There's lots of question marks and open things that we can decide. So on and off switches, you can say. But overall, this is a fixed recipe. So for instance, you can switch on or off rescaling, or if you do imputation, you can choose between mean and median, for instance. Right? But all of these become options. So you can express this pipeline as a vector basically of options, and then the architecture search or the pipeline search just becomes a matter of high parameter optimization. We can use any black box technique to then find the optimal pipeline. And this has been done for a lot of the techniques like AutoSklearn, which is a very well-known AutoML method that does something like this, AutoWeka as well, and even like AutoGrew Tabular, which is a very recent new AutoML system, does this in a very strong way. It has a very strong portfolio of things that it does, like classifiers it builds, and then builds a large stack of them together. So the search page is even easier, and they don't even do high parameter tuning, but they build it very robustly. Now, a question that you may ask, well, maybe we don't need to fix this architecture. Maybe we can learn this from experience. And I think that's totally true. I just haven't seen any work yet that really tries to learn the optimal structure of pipelines from lots of data. The same goes for neural architectures. So we typically have ways to do that. If we have to solve a quite simple problem, we typically stick to just sequential models, and we just select the number of layers, type of layers, and so on, which is good, easy to search, but it's often too simple, right? We can also use some kind of parameterized graph, which is of course more flexible, but it will be harder to search. Now, what we've seen from well-performing models is that they tend to have a repeated motive structure. We call them cells. For instance, if you look at inception, you can see it starts with input and stemming, and then it has 4 of these inception cells, then a reduction cell, and then 7 of these inception cells, and then again a reduction cell, and so on. So these cells are repeated, right? And that apparently makes models work well. So let's use that as a prior. So, and this is called the cell search space. So we assume a microarchitecture in which is just linear. It's just a sequence of cells, right? Just as we saw here at the bottom. Right? And then the only thing we need to do is to learn these cells. And this drastically makes the problem simpler. It's a perfect example of compositionality. Right? We break the hard problem down into smaller problems, and we solve the smaller problems much easier. Yeah. So this makes the search space much smaller. And also these cells, they can be learned at small subsets of the data. We don't have to always evaluate the entire network on the entire data set. We can test these small cells on smaller sets of data. Now, this doesn't pose a strong domain prior. Now, it has been shown that this works very well for most vision tasks, but of course, this won't work well for other tasks. And here again, the question is, okay, we've observed this and we use this, but maybe there are other structures, hierarchies, ways to compose neural nets that we haven't discovered yet, and that maybe we may want to learn. And so one case where the cell search space was effectively used was with NASNet in 2018. So there we learned these cells using a reinforcement learn-based search algorithm. So it starts with some hidden state, which is some kind of input, and then it decides to add things like a pooling layer, convolution layer, that adds them together, ends up with a new state, and then we choose a new state, we add more layers and so on. And after a while, we find certain cells, like this is a normal cell, and here's a reduction cell, and we train this on our data. Now, this got state-of-the-art results in ImageNet, but it was quite expensive. It used over 450 GPUs for 3 to 4 days. And this was even a cheaper version of an even more expensive version before. You can also use this in neuroevolution. So AmoebaNet, which is also one of the state-of-the-art ones in 2019 for ImageNet, did the same thing, but just used neuroevolution instead of reinforcement learning. And again, found new cells that worked very well for image classification. Interestingly, shortly afterwards, it was also shown that you can get equally good results using multi-fidelity random search. This is a random search in which you don't evaluate every random model on every full data set, but you evaluate many random ones on a small portion of the data set, and only the ones that work well on a small portion of the data set you try on large data sets, and so on. And apparently they got very good results just doing that. So this tells us that a lot of the power lies in the cell search space. It is a very strong, useful prior for these types of tasks. Another interesting prior is weight sharing. And this is taken to the extreme in these weight agnostic neural networks, to the extent that all the weights are shared, right? So all the weights in the network are the same, and the only thing you do is learn the architecture. There are extra biases, like there's a minimal description length, which means that like you prefer smaller networks over large networks. And there's also probably this Baldwin effect in evolution. So if evolution discovers a certain like submodule that's interesting, this sort of survives and gets spread out to other candidates and so on. But still, it's quite amazing that they can build working models without learning any weights. That's again gives us some indication that weight sharing is really, really important. So they've tried this for reinforcement learning tasks like this bipedal walker and this race car, which worked very nicely. You could inference, well, they've shown that you could also do this for image classification, but this tends to become very complex. It's not rediscovering convolutions in any way. Okay, now, first thing we're going to do for meta learning is to see whether we can learn these hyperparameter priors. One thing you can do, for instance, so assume that you want to use a black box model, a black box optimizer, like Bayesian optimization or evolution. You may want to reduce the number of hyperparameters that you need to tune. And so what you can do is you can change the values for all the possible hyperparameters and see what the effect is of the change on performance. If changing a variable, if changing a hyperparameter gives you a big effect on performance, then this hyperparameter is possibly important. And that's the idea behind this functional ANOVA approach. And so you can see that they've done this for all kinds of hyperparameters of neural nets. And from this, you can see which ones are likely more interesting to tune and which ones you may just leave at default and not touch. Follow-up work on that also said, well, this is true, but if you have a good default, then you may have, then changing it doesn't make sense, right? So what you do here is, first of all, you learn good defaults, which is an art in itself. After you find those, you then see, okay, how much can we still improve over this learned default, right? And then you can establish a tuning risk. For instance, here you see for perfecting machines like C and gamma have a pretty high risk, while tolerance and string have very low risk, for instance. Okay, now a short interlude about Bayesian optimization, because this will be very useful in certain ways. Bayesian optimization is a technique to optimize the hyperparameters. These hyperparameters are all numeric. What you do is, say you have 10 hyperparameters, so you have 10-dimensional space to search. Now imagine you only look at one, right? So say we have one parameter, for instance, the learning rate, right? So in this graph here. So what we do, we start off with randomly choosing a number of learning rates, right? And we evaluate those, and then we see here performance. So this is the first one, it gets this performance. This is the second one, it gets a higher performance. Okay, now we want to know which other learning rates may be better. So we fit a linear regression, a probabilistic regression function to these points, hoping that this will allow us to predict which other learning rates are going to be working well. Now, of course, if we just use a normal regression function, we will run to local minimum. So what we will do instead is this combination of an acquisition function and our model. So our model has to be probabilistic, so it gives us a mean and an uncertainty. And the acquisition function weighs off both. So it wants to give us a point where you have high expected performance, but also high uncertainty. And there are different acquisition functions you can use. The most commonly used one is expected improvement. Okay, once you have found this interesting point, you evaluate it. And you try this hyperparameter on your test data, and you'll get a new point here. And then you refit your surrogate model. The surrogate model is the name for this regression model that we fit to data points. Then we recompute the acquisition function. We have a new point, we evaluate that, and we continue. This is a very nice method, has very nice guarantees that it will find a good optimum in a limited amount of time. It works in all kinds of situations, and it was used in the original AlphaGo to tune the hyperparameters of the multicolored tree search that they used in there. Okay, now besides from being a good way to optimize black box problems, there is the model itself encodes information about the hyperparameters, right? And that's something that we can really use. First way, not a first way temporally, but a very interesting way to do this is this learning of a Bayesian expansion. So what you do here, so instead of learning this complex, expensive Gaussian process surrogate. Remember, Gaussian processes are cubic in the number of points and dimensions. So doing this for a very large search space becomes very expensive. So what you can do, you can use some kind of meta learning here. So given a large number of configurations and scores, you can put this into a neural net to then learn a Bayesian expansion. So what this does, it learns basically, so if you have a hyperparameter here which behaves exponentially, well, then we just take the log. Or if it behaves like a sine wave, we replace with a sine wave, whatever. So we learn a Bayesian expansion that transforms this hyperparameter search space into one which we can model with linear models, right? So this will be a higher dimensional space, right? So we take our lower dimensional space and we construct a higher dimensional space in which we can fit these hyperparameters with a Bayesian linear circuit. It's great because now we can do it very fast, and we have learned a very nice, we've learned the relationship between the hyperparameters. We can also transfer the circuit models themselves, and that becomes interesting when we have a new task. Right? So say we have built the circuit models for a number of tasks in the past, and now we're given a new task. Well, we don't know whether this task is somehow similar to the other tasks, but we assume that this information is still somehow useful. So what we do is we take the sum of all the circuit models on previous tasks, which gives us a new circuit model S here, and we use that to tell us which hyperparameter may be useful. After we've done that, we evaluate that, and then we see, okay, which circuit models were actually right, and then the ones which were right are given a higher weight. And so by doing this, by testing different configurations on your new test task, you learn these weights, and you learn how to combine the different circuit models. In rough terms, this means that you learn which tasks were similar in terms of whether the hyperparameters behave the same way on your new task as they did in the previous tasks. Right? So this is a very nice way to use this information. So you're not starting blind. You're actually starting from what worked in the past, and at the same time, you're learning how this task is related to prior tasks. Some other follow-up work, which looks very similar to what we discussed in the previous lecture on meta-learning. So in this case, remember we had these different algorithms. So here for every algorithm and for every task, we build a circuit model. And the reason we do this per task and per algorithm is because then the circuit models become simpler and are more likely to transfer well. So if you then are given a new task, again, we build a linear combination of all these prior tasks and the new task. And then we evaluate those on the new task, and then we learn these weights as before, and that way we can again have a new super surrogate that we can use to tell us which high parameters will work well on a new task. Okay, another thing we can do is warm starting. So the idea is here that instead of starting from a random neural architecture or a random pipeline, we start from ones which have been shown to work well in the past. Now, this requires us to have some measure of similarity between tasks, right? Because we want to reuse pipelines and architectures from similar tasks, but not from totally different tasks. So you need a way to establish similarity between tasks. There's a huge number of ways to do that. A lot of this work was done just in the last year. So for a long time, we were using these hand-designed statistical meta features, which get you some, they're useful and they get you some power away. But recently, we have also been looking at how we can actually learn good task embeddings. And there's different ways to do that. So first of all, there's task2vec, which is a task embedding for image data, which works with a probing network. So you push the data to a network and you look at the response, and then you put it into the efficient information matrix, which then gives you a kind of embedding for image data. You can use optimal transport, which is shown here at the bottom. So say you have there's A of digits, here there's a B of clothes. You want to see how similar they are, and you compute a similarity measure but based on comparing probability distributions of these two tasks, two data sets. You can also construct metadata embedding based on a textual data set description. So if data has a textual description, you can push this through a transformer, build a text embedding, and then you can use that to measure some different distance between data sets. There's also dataset2vec. This one looks at batches of data sets, which kind of solves the problem of having data of different sizes, and then intelligently combines those into a vector that you can then use to measure distances between tasks. And there's also this distribution-based invariant deep networks, which also learn some kind of embedding of the tasks. Okay. So this is all very new work. There is no data yet on which one works better or how to combine these in certain ways, but it gives us some oxygen to do work in this area. Okay, so how can we use these task embeddings? So one thing we can do is kind of a K&N approach, which has been very successful for a very long time. So what you do is, given a new task, you kind of see which prior tasks in memory are similar to my new task, and then I just use the pipelines or the architecture that worked well on those similar tasks. So for instance, AutoScikit-learn does this. So if you give a new task, it has this memory of over 500 OpenML tasks, and then the best pipelines on these tasks. And when you give a new task, it just looks up which were the good pipelines and then starts the search with those. So it uses Bayesian optimization, but instead of starting Bayesian optimization randomly, it starts with pipelines that worked well before. And that gives a very substantial boost. And because of this, it also won several AutoML challenges. Another thing you can do is probabilistic matrix factorization. So here you learn embedding for both tasks and configurations. So imagine that you have scores. You've evaluated different configurations, different pipelines, different architectures on different tasks, and you put them into this big matrix here. And you see the scores of a configuration as kind of a rating, right? If you remember how collaborative filtering works. This ends up being a sparse matrix where for every task and every configuration, you get a score. And then you learn latent representation using matrix decomposition, probabilistic matrix factorization in this case, which will give you a latent representation of your configurations and your tasks. Right? So if in this case, we look at the latent description of these configurations, we can see every dot here is one pipeline, and we can see which pipelines are good, they cluster together, which pipelines are bad, they cluster together. So this latent representation gives you some information about how configurations compare to each other. And you can actually use that to then build a new search space. Right? So instead of having maybe 1,000 possible hyperparameters, you can learn a lower dimensional latent space, in which is easier to model how these hyperparameters behave. Another segue now is about DARTs, which is a technique for differentiable neural architecture search. So the way it starts with a one-shot model. So it's a fixed structure for your neural net, and the user has to provide this, right? So it consists of a number of states with gaps in between, and you can fill in these gaps with layers, for instance, a convolution layer, max pooling, or do nothing. Okay, and this creates a space of possible neural networks. Then you learn this through bi-level optimization. So you give each of these links here a weight alpha. Then you try some of these weights on small part of the data. You get the score back and use the score to then update the weights alpha. Then you use that to do another mini batch, update the model weights. So you optimize the model weights and these weights alpha at the same time. So it's a kind of bi-level optimization. And through doing that, you converge into a file network. One thing you could do is you could warm start darts. So instead of starting from this use to find one, we can learn a good model to start from. So in this case, we looked at different architectures learned at different data sets. These were all image classification data sets. And from that, we built this initial model. So this has a number of states for ourselves. And between them, we have options like max pool, average pooling, skip connect, and so on. Okay. So we learned this based on previous trained models. And then we can then use that as input for darts, and then we can learn and find good architectures much more efficiently. Right? So here results for AppGraph and words. Right? So you can train this initial model on one data set and transfer it to other data sets. Last part are meta models. So these are models that explicitly you use to build entire models or components of the model. The oldest technique here comes from algorithm selection, which has been done for a long time. And you can build different models. They don't build entire pipelines or architectures, but they help you make certain decisions. So for instance, you can have zero-shot models which predict the best configuration given some meta features, right? So you have your data set, you measure some things about the task embedding, right? So you give the task embedding then to the meta learner, which will then tell you which is the best algorithm to choose, for instance, or which is the best imputation method to use, or which is the best feature selection to use. Right? So you can train these meta learners to answer these kind of questions. You can do the same thing with ranking models. If you're interested in the ranking of possible classifiers, you can do it as well. You can see which algorithms configurations you should consider, which one you should tune, yes or no. Or you can even pick runtime. And this happens to be quite doable. So if you want to search a large space of possible models, you could train such a meta learner to tell you which ones are going to be fast, which ones are going to be slow. And you could use that, for instance, to pay more attention to the fast ones first before you're going to put really serious effort into also evaluating the slower networks or the slower pipelines. You can also learn model components. Like you can actually learn nonlinearities like activation functions. So in this work, so you used a reinforcement learning based search over a space of likely useful activation functions. So they did things like having, in this case, like a logit function, multiplications, sine waves, whatever. So they built a search space of possible functions, and then they searched that to see which activation function actually performs well on a group of tasks. Right? And there's some interesting results there. For instance, they discovered this swish activation function, which has been shown to outperform ReLU on this group of tasks that they had. You can also learn optimizers. So an optimizer is basically just an update rule. And so you can use reinforcement learning-based search or other techniques to search the space of possible update rules. So again, you define a search space with a number of components of update rules. So obviously, the gradient should be in there, but you can combine it with other things as well. And so if you do that, you can learn new optimizers, for instance, the power sign here, which is defined as the exponent of the sine of the gradient times the sine of the moving average times the gradient. And they've shown that this actually works better than Atom or MRS prop. But the more general message here is that you could learn these things, which is interesting because you then don't have to decide what to do. You just learn the best optimizer and the best linearity for your task. Or vice versa, it could be interesting to just learn these on a bunch of tasks and then discover new things like these functions and then reason backwards, okay, why would this work? This could also inform us how to do better machine learning. And lastly, you could also use this to learn acquisition functions for Bayesian optimization, which are more robust. Okay, another interesting technique you can use here is multicolored tree search and reinforcement learning. And this is a method called alpha D3M. There's also one called Mosaic. And this operates through self-play. So in this case, you have a multicolored tree search which generates pipelines. So this doesn't work for architectures, but it works for pipelines. So every path in this tree here is a pipeline. You give the pipeline, you evaluate it, and you give it to a neural net. The neural net here is an RNN that has to predict action probabilities. So these are things like adding a component or removing a component from the pipeline. And it gives these action probabilities to the multicolored tree search, which will then use that to sample the next pipeline to train. You also give the activation, the evaluation of the pipelines, and the neural network also has to predict how well a pipeline will behave. Okay. Now, because this tends to end up producing a lot of bogus pipelines, you want a grammar as well to avoid invalid pipelines. So once you have this, you can just do self-play, right? You can keep this running over and over and over and over again until the network learns how to build good pipelines for a new task. And the nice thing is that after you've trained this on one task, you can keep the weights and then try it on a new task. And then hopefully that will thus give you good initialization for solving the new task faster. There's also neural architecture transfer learning. So in this case, we have a task embedding, like a source task, and then we feed it into an RNN, which then has to, so an RNN controller, and this will then produce, actions. So you're building in a reinforcement learning agent. And there's prior information from this previous task. So which was a prior task, which were the prior actions, giving that to your RL agent allows it to learn this new RL controller faster. Well, the controller aims to learn the agent faster. In this work, we use meta reinforcement learning for neural architecture search. So the goal here is to build a model for image classification through neural architecture, through meta reinforcement learning. So what we do is we train an agent. What the agent has to do is certain actions like adding a convolution layer at some part in the network. And you do that through these neural codes. So every neural code is a certain action that you do, like adding something or removing something from the network. And then you train the agent to learn how to do this. So you train an agent how to build a neural network for a certain image classification task. And what this gives you is that, well, of course, in the beginning, this is going to be very expensive because, well, RL agents don't learn that fast. And evaluating that is expensive. So you will have to spend a lot of time in the beginning to train this agent. But after you've done that, you can transfer, it has learned how to do that. And so if you give the new task, it can actually effectively transfer the information and learn the new task faster. And so what we see here is we have 3 of these image classification data sets, like Omniclot, which is quite simple, Flower, which is more complex, and DDT, which is about textures, that's even harder. And so after the first task, we see that, well, we are the blue ones here, MetaRel. MetaRel doesn't do much better than just a DQN reinforcement learner, because, well, it has no extra benefit over it, of course. But because it can transfer, because it's a meta reinforcement learner, you can transfer to a new task. And at the new task, you see it already starts outperforming the DQN. At the third task, it becomes very apparent. Also interesting to see is that if you look at the policy entropy, is that for the first task, well, the entropy is still quite high, and only at the end it lowers a bit. And then if it goes to the second task, you see that it immediately drops. So it uses information from the previous task to learn this new task faster. And then when it gets to the new task, which is harder, well, first the entropy increases because this task is quite very different from what we saw before. And then it learns how to solve the task as well. So you can see there's definitely a transfer of information across tasks. And finally, meta-analysis. This is a nice method that combines MAML with neural architecture search. And in actuality, it combines Reptile with darts. So remember Reptile from a previous part of this tutorial. So there we use gradient-based meta-learning to learn a good initialization for a network. And remember that darts wants to learn this connection weights alpha, right? And so you can train both of them at the same time. And so you basically have, this is just, this image here is simply MAML, but in a different representation, different structure. And basically what we do, every time we have to update the weights or the meta weights, we also update the weights of darts. Right? And by doing those two at the same time, we end up with a method that can do fusion learning, but also learns to build the best neural nets for doing that. Okay, with that, we've become full circle with the previous lecture, previous part. Thank you for your attention and see you in the next part.